Welcome to the lecture series on numerical methods, and till now we have discussed about this finite difference operators. So, now we will continue about this central difference table, and we will start about the central difference approximations how we can use for different values here. So, in the tabular form, if we will just write the central difference table here, the central difference can be written as, if I will just write I as the value here, there is 0, 1, 2, 3, 4 here, and the respective tabular values are like xi here, then I can just write this tabular points as x0, x1, x2, x3, x4 here, and associated variable values are like y0, y1, y2, y3, y4 here. Then the central difference approximator approximates that delta of yi as, since we are just expressing delta of f of x as f of x plus h by 2 minus f of x minus h by 2, I can just write delta of yr as y of r plus half minus y of r minus half here. So, if I am just expressing this one in this form, then I can write this first approximation as delta y of half here. Then second approximation I can just write, since we are just considering the average of these two here. So, first average, if I will just consider 1 plus 0 by 2, since delta of yr means delta of y of half here. So, delta of y of half means y of half plus half, this will just give you y1 minus y of half minus half means this is just giving you y0 there. So, that is why if you are just taking the difference of these two here, then we can just write that as delta of y of half here. If you will just take the difference of y2 minus y1, I can just write delta y of 3 by 2 here, and for y3 minus y2 I can just write delta y of 5 by 2 here. If I will just take the difference of these two, I can just write delta y of 7 by 2 here. Since delta of y by y of 3 by 2, I can just write this one as in the form of y of 3 by 2 plus half minus y of 3 by 2 minus half here. So, it can be written as y of 3 plus 1 by 2 here minus y of 3 minus 1 by 2 here. So, it can be written as y2 minus y1 here. So, obviously y2 minus y1, it is just written as delta of y of minus 3 by 2 here. Similarly, y1 minus y0, it can be written as delta y of half here. And if we are just taking the difference of y3 minus y2, it can be represented as delta y of 5 by 2 here. And if you will just take the difference of y4 minus y3, it can be expressed as delta y of 7 by 2. Again, if you will take the difference of these two here, so it can be expressed as a delta square of yi here, and I can just write this one as a delta of y1 here. Since if you will just take the average of this is delta square of y of 1 here. If I am just assuming this one, this means that delta of y of 1 here. So, if I will just take delta of y1, so delta of y1 I can just write as y of 1 minus half, plus half minus y of 1 minus half here, and it can obviously written as y of 1 plus half minus delta y of 1 minus half here, and I can just write this one as a delta of y of 1 plus half, I can just write this one as y of 1 plus half minus y of 1 plus half minus half here. Similarly, minus, it can be written as y of 1 minus half plus half minus y of 1 minus half here. So, obviously, it can be written as 1 plus 1, this is a y2 minus y1, since it can cancel it out. So, directly I can just write this one as y2 minus y1 minus y1 minus y0. So, if you will just see this del square of y1 is nothing but we can just write y2 minus y1 minus y1 minus y0 here. So, obviously, this is just coming as del square of y1 here. Similarly, we can just write this difference of these two as del square of y2 here, and the difference of these two we can just write del square of y3 here. If we will just take the difference of again these two here, so it can be written in the form of a del q of yi here. So, I can just write this one as del q of y of 3 by 2, and this one can be written as a del q of y of 5 by 2 here. If I will take one more difference here, del to the power 4 of y here, so then I can just write del to the power 4 of y2 here. Since if we are just taking the central difference form here, so the values are associated here as 0, 1, 2, 3, 4, and the central value is taking as 2 here. So, that is why the final form, the central difference approximates the value at the center of the table only. So, next we will discuss about this Newton's forward difference formula. Basically, we are just using the set of tabular points that is in the form of here as x0, x1, x2 up to xn here, and all of these tabular points, that is x0 to xn, are equally spaced. This means that x0, x1, x2, x3, likewise we are just writing up to xn here. This means that if all points are equally spaced, we can just write xi equals to xi minus 1 plus h here, or we can just write this one as x1 equals to x0 plus h, x2 equals to x1 plus h, likewise xn equals to xn minus 1 plus h here. And we can just write all these points that is in the form of like x0, x1, x2, x3 up to xn. If these are the given set of tabular points, we can just express all these points should be equally spaced. This means that h is the space size in that locations. Then we can express this associated variable values as y0, y1 up to yn there. Then we can express this Newton's forward difference formula as y of xp. This means that any particular point, if we want to evaluate at any of the middle of these intervals, then we can just write this formula as in the form of y0 plus p delta of y0 p into p minus 1 by factorial 2 del square of y0. So, up to p into p minus 1 into p minus 2 up to p minus n minus 1 divided by n factorial and del to the power n y0 here. So, basically if we want to evaluate any point within this particular interval, then we can just express this point as xp as x0 plus ph here. And if we want to express this function in the form of a polynomial, we can just replace at any point x, means we can just replace this p as in the form of x there, and we can evaluate this formula in the form of a polynomial there. So, in a complete form, if we want to derive this formula, then we can take this Taylor series expansion, which is used for this shift operator. So, if we want to express this Newton's forward difference formula in the form of p here, this means that Newton's forward difference formula can be written as y of xp, that is at any point within this interval x0, x1 to up to xn. If we want to find at any point then we can just write this formula as in the form of y0 p delta of y0 p into p minus 1 by factorial 2 del square of y0 plus up to p into p minus 1 up to p minus n minus 1 by n factorial del to the power n of y0 there. Especially if we will just see in the tabular point here, this is starting at x0, x1, x2, x3 up to xn here. So, if any point we want to evaluate at the beginning of the table, we can use Newton's forward difference formula here. Basically, if we are just writing this point as x, this means that x has a coefficient there. So, that is why we are just expressing that is in the form of xp here. So, usually xp can be written as x0 plus ph, since all of these points we are just expressing that is in the form of xi equals to xi minus 1 plus h here. And wherever we will just start this computation, we have to choose the beginning of the point as x0 there, since this p value should be lies between 0 and 1 here. Especially if you will just consider, then we can just evaluate this formula there. This means that if we want to find y of xp in a functional form here, we can just write this one as y of x0 plus ph, and it can be expressed as e to the power p of y0 there, and e can be expressed in the form of 1 plus delta here, since whenever we are just expressing delta of f of x, usually it is written in the form of f of x plus h minus f of x, and hence it can be written as e of f of x minus f of x, and it can be written as e minus 1 of f of x there. So, delta can be expressed as e minus 1. So, that is why we can just write 1 plus delta equals to e there. So, that is why we can just replace here e as 1 plus delta whole power p of y0 here. And if you will just expand this term, then we can just write this one as 1 plus p delta plus p into p minus 1 by factorial 2 plus p into p minus 1 into p minus 2 by 3 factorial delta square here, this is delta q here. So, likewise it will just continue and operated on this y0 value. So, I can just write these values as y0 plus p delta of y0 plus p into p minus 1 by 2 factorial del square of y0. Likewise, I can just express, and if I want to evaluate this function in a polynomial form, that is in the form of x there, I can just express this as, I can express this p in the form of here, since x is expressed, xp as expressed as x0 plus ph here. So, this xp is nothing but any point which is existing within this interval x0, x1, x2 up to xn in any of these intervals. So, this xp is situated. So, commonly we can just consider this point as x there. So, which can be expressed as x0 plus ph, and I can just write p as x minus x0 by h there. Similarly, if I want to write p minus 1, this can be written as x minus x0 by h minus 1 here, and which can be written as x minus x0 minus h by h here, where I can just write x minus x1 by h here, since x1 can be expressed as x0 plus h here. Similarly, I can just write p minus 2, that is in the form of x minus x2 by h there. In each of these formulations, I can just express this one in the form of p. If I will just replace p in terms of x there, I can just obtain a polynomial that is in the form of x there. So, if it is asked to evaluate any polynomial which is existing at any point which is existing at the beginning of the table, then we can express that as a polynomial of x in Newton's forward difference formula. So, this is the Newton's forward difference formula, whatever I have just discussed. Then we will just go for this Newton's backward difference formula. In the Newton's backward difference formula, especially we are just using these tabular values at the end of the table only. So, if you will discuss about Newton's backward difference formula, especially if the set of tabular points are expressed in the form of x0, x1, x2 up to xn, and the corresponding associated values are y0, y1, y2 up to yn, and each of these points are equispaced. This means that x0 minus x1 difference will be h and x2 minus x1 difference will be h. Then we can just write Newton's backward difference formula as y of xp as y0 plus p nabla of y0 p into p plus 1 by factorial 2 nabla square of y0 p into p plus 1 up to p plus n minus 1 by n factorial nabla to the power n of y0. We have to choose y0 in such a fashion that y0 should be existing at the end of the table. So, previous values can be considered as y of minus 1, y of minus 2 up to y of minus n there. Since this value y0 will exist at the end of the table only, and we can express here xp or x as x0 plus ph there, where p can be written as x minus x0 by h in that position also. And if we want to express this function in a form of shift operator here, this means that y of xp can be written as e power p y0 here, since xp can be expressed as x0 plus ph, and where we can just write e of xp means e of x0 plus ph, which can be expressed as e to the power p of x0 here. So, since we are just expressing this function, that is e of f of xp here, or e of xp means it is e of x0 plus ph here. So, if we want to express this one, that is y as a function of x here, that means y of x0 plus ph here, and e is operated on y of p here. So, that is why it is written as e to the power p of y0, this one. So, that is why if we want to express this one as in the form of e to the power p of y0 here, so it can be expressed as in the form of nabla here, that is usually nabla of f of x is written in the form of f of x minus h, and it can be expressed as f of x minus e power of minus 1 of f of x, so this one. So, I can just write 1 minus e inverse of f of x. So, this can be written in the form of like nabla equals to 1 minus e inverse, or I can just write this one as e inverse equals to 1 minus nabla here, and e can be written as 1 minus nabla whole inverse. So, if I will just write here, this can be written in the form of 1 minus nabla whole to the power minus p of y0, and it can be expanded in the form of like 1 plus p nabla plus p into p plus 1 by factorial 2 nabla square. So, likewise operated on y0 here. So, in a combined form I can just write y0 plus p nabla of y0 p into p plus 1 by factorial 2 nabla square y0 plus this will just continue. So, this is the representation for Newton's backward difference formula, and if we will just write this is in the form of a polynomial here. So, then we can just estimate this series as in the form of like p equals to x minus x0 by h here. So, similarly I can just express p plus 1 as p equals to x minus x 0 by h here. So, p plus 1 can be written as x minus x 0 by h plus 1. This can be written as x minus x 0 plus h by h here, this one. So, I can just write x minus x 0 minus h by h. I can just write x minus x of minus 1 by h, this one. Similarly, I can just write p plus 2 also there. So, p plus 2 can be written as x minus x of minus 2 by h there, and in this form we can just express this as in the form of a polynomial, that is taking all of these backward points. So, whenever we are just discussing this Newton's forward difference formula or Newton's backward difference formula, there is always existing a error term there. Since whenever we are just writing this series expansion, so finally we are ended off these terms up to nth term there. So, after the nth term, so there will be some extra terms are there which we are just neglecting there. So, if that terms we will just include, so in a complete form we can just write this series expansion as y of x equals to your series expansion, that is y of xp plus Rn term there, that is the remainder term. So, in each like Newton's forward difference formula, backward difference formula, always there will be a associated error there. So, if we want to calculate this error, first we will discuss about a generalized error approximated formula here. So, if you will just write this error of approximations, so let us consider, suppose a function y equals to f of x is existing at k plus 1 point, suppose that is x0, x1 up to xk and xk plus 1 points, and each of these points these functional values will be associated also like y0, y1, y2 up to yk plus 1. Then if y of x is satisfied at exactly these points with a polynomial, since we are just discussing this one in a polynomial sense here. So, y of x is approximated with p of x at x0, x1, x2 up to xk here, since k plus 1 points are existing. Then if we will just approximate this function here, that is y equals to f of x is a function which is approximated or interpolated with a polynomial p of x here at exactly at these points like x0, x1, x2 up to xk points. At each of these points the difference between this y equals to f of x and p of x is exactly 0. But at all other points we can just find a difference is existing. So, if this difference is existing, then there will be a error term is associated with each of this function and the polynomial whenever we are just approximating them in a polynomial sense here. So, if we will just write this in a complete form, so y of x can be written as p of x plus r of x term here. So, usually this y of x and p of x exactly equals at each of these nodal points or tabular points, but at all other points there exists a difference between this y of x and p of x where r of x is existing. So, if we will just write here r of x as in the form of like kx into w of x, since at all of these tabular points we are just approximating that f of x equals to p of x there, y equals to f of x. So, if exactly it will be equal at these points, so this function should be 0 at exactly these points also. So, that is why we can just express this Rx term as in the form of kx into wx, where wx will be associated with this term like x minus x0, x minus x1, x minus x2 up to x minus xk, where we can just satisfy y of xi equals to p of xi plus r of xi. But if we will just approximate this function exactly at these points, we can just consider a point which is existing within this interval, suppose x bar. At that point this function is also satisfying that x bar value. So, if you will just consider that function as x bar value, so we can just choose kx as kx bar at that point exactly, that k of x bar equals to f of x bar minus p of x bar by w of x bar, since at that point these values will not satisfy. Maybe that point lies here or here or here, somewhere else it may lies. Since exactly at these points we are just observing that y of x, p of x and w of x takes the 0 value. We are just considering x bar as a point within this interval somewhere that should satisfy the value that is in the form of k of x bar equals to f of x bar minus p of x bar by w of x bar there. So, we can just approximate this function that at that point exactly f of x equals to p of x plus w of x into k of x bar. So, where we can just write this remainder term r of x as w of x into k of x bar. So, if we want to determine the value of k of x bar, let us consider this function that as phi of x equals to f of x minus p of x minus f of x bar minus p of x bar by w of x bar into w of x. Since w of x takes the values that exactly f of x and p of x are satisfied at x0, x1 to xn there. So, if these are the k plus 1 points where phi of x satisfies this value, then we can just assume that phi of x will be satisfy 0 value at k plus 2 points, since x bar is the extra point there. So, if x bar is the extra point and x0, x1 to up to xk are k plus 1 points, then phi function will satisfy 0 value at k plus 2 points. So, if you will just consider in a polynomial sense, that is satisfying Rolle's theorem, phi of x will vanish at k plus 2 points, and then phi dash x must vanish at k plus 1 points. Similarly, if you will just go ahead, we can just find that phi of k plus 1 will vanish at 1 point only. Suppose that point is zeta, suppose. Since p of x is a polynomial of highest degree k, so if you will take k plus 1th derivative, p of x will be also 0. Similarly, f of x will be also 0 at that point, but phi of k plus 1, since at least at one point the k plus 1th derivative of phi function, that will give you also a 0 function there. So, that is why we can just write phi of k plus 1 zeta equals to 0. So, then we can just express f of x bar minus p of x bar by w of x bar, this equals to f to the power k plus 1 zeta by k plus 1 factorial. So, if you will just compare both these equations, that is expressed as equation 4 and equation 7, we can just get that k of x bar can be expressed as f to the power k plus 1 zeta by k plus 1 factorial. In a complete sense, if we want to write this function or this remainder term, so r of x can be expressed in the form of w of x into f to the power k plus 1 zeta by k plus 1 factorial here. So, if I am just writing here r of x, this can be written as w of x into f to the power k plus 1 zeta by k plus 1 factorial here, where zeta should be lies between x0 to xk here, and wx term is written in the form of x minus x0, x minus x1 up to x minus xk here into f to the power k plus 1 zeta by k plus 1 factorial here. So, if we are just expressing this generalized error function, that is expressed in the form of like x minus x0, x minus x1 to x minus xk into f to the power k plus 1 zeta by k plus 1 factorial here, where zeta should lies between x0 and xk. So, next class we will just continue this function that can be expressed at central difference table points, and we can just approximate these values in a central difference approximated form. That central difference approximation terms includes like Gauss forward difference formula, backward difference formula, and Bessel's formula and Stalling's formula. That will just continue in the next lecture.